time.
It's weird because some people I've got to include and other people that just slide in without me saying you're welcome. It's quite weird. Most of you this evening I've had to give access to the meeting, but Benny he snuck in. Anyway, okay, we are recording, I believe. Thank you, Jesus. Let's pray. Father, we bless you. We thank you, Lord God. We love you. We worship you, Father. We adore you. You're so special in our lives. We pray that as we study this evening, that you'll give us revelation and understanding, Lord, that you'll bring liberty and understanding to our hearts, Father, in Jesus' precious name. Help me, Lord, to bring tonight over with clarity and understanding, and help us, Lord, to have ears to hear and eyes to see and grasp with understanding in Jesus' name. Amen. I'm praying tonight particularly for understanding because tonight is as scientific as it's going to get. So I've tried to make this as unscientific as I possibly can because I'm not a scientist. But tonight we're doing dating methods. And so I have to explain the basis behind the dating methods so that I can make the assumptions behind the dating methods more clear. So I've got a lot to get through, but I'm not going to rush tonight. Because I think it's important that we understand it. So if necessary, I'll drag this into a second week, but hopefully we'll finish. So just to recap, the last 2 weeks we've gone through, we've looked at the fact that, first of all, that evolution is a religion and not a science. We looked at the fact there's nothing scientific about it. And then last week we looked at the significant problems posed by evolution, if you want to think of that as a source of the origin of all things, and we saw how little it says about the origins, and we looked at how many of the links are missing, and we do all that. And it was really funny, we did all that. It was really funny. I was watching a program on the evolution of species on TV the other day. It was a BBC TV program, and some doctor has taken this fish that can live, a fine little thing with little fins on the side underneath, that can either live on land or in the sea. It's quite amphibious, and they've raised the sample section of some in the water, and they raised the other ones purely on the land, and they've looked at how they grew up differently, and I was quite astounded by how they think, and there's some differences to the ones on land, mostly around the pectoral fins, because these animals had to walk on their pectoral fins, so they've developed musculature that in their lifespan they've got stronger pectoral muscles than the other ones. But one of the things that was completely ridiculous was they said that the muscles that link the head of the fish to the fish's spine were slightly weaker than the ones who grew in the water, and that was, in their view, the precursor to a rotating, revolving mammalian head, which you don't get on fish. So because the muscle was weaker. It just amazes me how they look for things where there is nothing. So I had a good chuckle. Okay, so let's talk about the dating methods. And please, as I said, I'm going to try and be as unconfusing as I can. If you need to ask questions, we will have a Q&A afterwards, and you can maybe just make a note of them, and I can get into more detail. Now, to start off with, every dating procedure that you use involves the same basic procedure. I'm going to keep referring to my notes tonight because I don't want to say something that's confusing. And the concept behind dating is it's not a difficult concept to grasp. It's really a simple thing. There may be, and in fact generally is, only one legitimate way to interpret data in terms of how you date stuff. So let me start off. I'm going to deal with the two primary dating methods that evolutionists or scientists use to date fossils or anything really. But before I do that, I want to deal with just a generalization, a sort of overview of what the dating process looks like, any dating process. And there's under normal circumstances, there's 4 steps to dating something. And it's true of almost anything. I'm not just talking about how you would date a rock. It's the same way how you would date Benny. How you would date anything. This is a general process. So number 1, there's 4 quick steps. You have to observe the present state of the rock or the system that you want to date. Whatever it is that you're trying to date, you've got to observe it in its present state. Now that is actually science, because remember, science is observable only in the present. So scientifically, they can observe the state of something in the present. And now this all makes sense in a little while. I've got a great parable to explain this to you. The second step is that you have to measure the rate of the process that is aging the system. So you've got to measure the rate at which the system is aging, okay? That is also science, because you observe that in the present. So you look at whatever it is, and you look at the cabbage right now, or the carrot, and then you observe it for 6 months, and you observe the speed at which it changes, at which it ages. So if you're observing a human being, it makes maybe more sense. You observe the rate of change or the rate of aging in the process, yeah? And that gives you an idea. It's also science. It gives you an idea of how fast aging occurs or change occurs in any given process. The third and fourth system is utterly unscientific, okay? The third and fourth steps. Although the third step has some validity. So the third step is you have to make some assumptions about the past history of the item that you're trying to age, the rock or the system. Yeah. So because you couldn't see the past history, you can't see, if I start observing something today, I can see what it is in the present, and I can see the rate at which it ages, but I can't see how it aged before I started watching it. So the only way I can do that is I can make some assumptions. Now, that is not science. It is called model building or data modeling. It's about making models, projections going backwards based on some assumptions you make and the data you've observed in the present and the speed at which it alters in the present. Okay? So you now, by doing that, by building data models, you're trying to create a reconstruction of an unobserved history. You're trying to say, because it happened like this going forward, we've observed this to happen, and I'm making some assumptions about the past, I can now understand how it used to age, okay? And then the fourth step in terms of aging something is you calculate how long it would take for the present process operating through the unobserved past to produce an existing state. Yeah. So you say, I look at the present, I calculate, I observe how quickly it ages. I then make some assumptions about how it has aged, and I can now calculate, based on those assumptions, how long it would have taken for it to get to the present state. So that's literally just interpretation. It's not science. It's interpretation based on data modeling, which is based on assumptions of an unobservable past, based on the science that you can observe in the present and the future. Not the future, the present, and the process at which something ages. So that's the simple process by which any aging of a system or a rock or an item would occur. Okay, now in terms of helping us understand this process, I've got a really good metaphor that I found. I can't claim this metaphor to be mine. It's a parable, at least. I found this parable in a book about 15 years ago, and I forgot to write down who wrote it. So if the person's listening, forgive me. I'm just using it. I'm not stealing it. So it's called the parable of the potato baskets. Okay. So remember what I said in terms of the 4 steps, yeah? So suppose that as a scientist, let's assume you're a scientist, you enter a lecture hall to attend a lecture, a scientific lecture, and as you arrive, you see me sitting on the platform with a basket of potatoes in front of me, okay? As you sit down, you notice that the clock in the lecture hall is at 12 o'clock. While you're sitting there, I take a potato out and I start to peel it. And when it's finished, I put it back in the basket, and you observe that it's now 1 minute past 12. Okay. I then take another potato out and I peel that and I put it back, and you're now watching and you see it's now 2 minutes past 12. And so I do 4 or 5 potatoes, and I do all of them with 1 minute each to peel them. So what you've seen is you've observed the present state. There's a basket of potatoes. You've observed the rate at which those are changing. They're becoming peeled potatoes at the rate of 1 per minute. So you've made a judgment on how fast the change occurs, okay? So at some point you ask the question, how long is this nut going to sit there and peel potatoes? In other words, you want to know how long I've been sitting so that you can calculate with reasonable assurance how long I'm going to sit, okay? So the question is the same that a scientist asks when investigating the age of a rock or the age of a system. A system, when scientists talk about systems, they're talking about life systems or vegetation systems, or so any system that you can age, yeah? So they're going to ask, how old is the rock? How long has the tree been growing? How long has the river delta been building up? They're interested in the age of something. How long has this process been going on for? And so the question back to my parable is, how are you going to determine how long I've been peeling potatoes? Now we're getting into the third step. We're now going to make some assumptions about your unobserved past. How long have I been sitting in the lecture hall peeling potatoes that you haven't been able to observe before you came into the room? So there's a number of things you might do. You might come up to my basket and observe how many potatoes are in the basket. And you might observe, for example, that there are 35 peeled potatoes. Yeah? And so you've observed me in the present peeling the system, peeling potatoes at a rate of 1 a minute for 5 minutes. And so you've measured that rate, so you can then logically make an assumption that because it took me a minute a potato and you've watched me do 5 and there's 35 in the basket, that I've been peeling potatoes for 35 minutes. The 5 minutes you watched me do it, and if you take the same rate I used to peel those 5 and you make an assumption, a number of assumptions going backwards, and I'll get to those assumptions, you can assume that the other 30 also took me a minute each, and therefore I've been peeling potatoes for 35 minutes, 5 of which you observed, 30 of which you didn't observe. So the system, in this case, how quickly a potato changes from being with a skin on it to being peeled, that's the system. You might observe that the system is 30 minutes old, plus the 5 minutes you've been observing, it's 35 minutes old. But the question is, are you correct? Now, in order to derive that conclusion, as I said, you've had to make certain assumptions. Let's look at the assumptions you've had to make. And there are three. There are 3 key assumptions that you make that I'm going to talk generally about now, and I'm going to refer back to the parable of the potato so that we can understand them. So the first assumption that you have to make is that you have to assume that the past rate at which potatoes were peeled is the same as the present rate. So the rate at which you observe me peeling potatoes, you're assuming that I've always peeled potatoes at that rate. What happens if when I started, I didn't know how to peel a potato, so it took me 5 minutes to peel the first one. And as I become more adept at peeling potatoes, I'm peeling potatoes faster. Or the alternative is true. What happens if I was really efficient the first 3 or 4 because I was fresh and my fingers were feeling quite flexible, and I peeled the first few potatoes really quickly. But now my fingers are getting stiff, I'm getting bored, it's getting monotonous, and so my rate of peeling potatoes is slowed. You see, you can't know whether the rate was faster or slower than what you've observed. So you have to make an assumption that the rate you've observed the process to age in or to change in, that rate of age or change has always been that way. So is it reasonable to assume that? Not necessarily. Okay. As a matter of fact, that's not the first assumption for the scientists in the room. The first assumption is you've assumed time moves in a linear fashion. You've assumed that 1 minute now is always been 1 minute, that at some point in the past, 1 minute wasn't faster or slower than what we know to be 1 minute. Just because time moves in a linear fashion in our world, in our day, in our observable time present, doesn't mean time has always moved in a linear fashion. But that's for the scientists amongst us. So that's the actual first assumption you've got to make. But in reality, the first assumption is you're making an assumption about the rate of the potato peeling having been constant. That's the first assumption. I said there's 3 assumptions. The second assumption that you've got to make is that and it's really a question that you've got to ask, is you've got to ask, have any peeled potatoes been added to or removed from the basket? You see, you're making an assumption that when I started peeling, there were 35 unpeeled potatoes in the basket. And now at the end of the process, there are still 35 potatoes in the basket. But what happens if in the beginning there was only 4 potatoes and someone came in, saw that I was peeling potato, sorry, I would have to say 7 because you've observed me doing 5, came in, saw me peeling potatoes and threw all their peeled potatoes in my basket? What happens if someone came in and saw that I'd peeled loads of potatoes, took them out and went off to make roast potatoes with them? And now I've only got 35 left. You see, you're making an assumption that no one added to the system or took anything away from the system in your pre-observed times, in the time before you were able to see it. So you have to make an assumption that in the unobservable past, nothing was added to the system and nothing was removed from the system that may have affected the rate of aging. Do those sound like 2 logical assumptions to you? Okay. The third, and again, you have no way of ascertaining that because it was unobserved. So the third assumption that you have to make, and again, it comes in the form of a question, and I've kind of touched on it it's how many peeled potatoes existed in the basket before I started peeling them? Maybe there were 25 peeled potatoes in the basket. I came along and saw 10 unpeeled ones, thought, you know what, I'm a bit OCD, I'm going to make these look the same. Or, hey, my wife's peeling potatoes, let me help her. And so I carry on peeling potatoes. You don't know how many peeled potatoes existed before I started the current system that you're observing. Yeah? No way of knowing that because it happened in the unobservable past. So let me sum up those 3 assumptions that you have to make about any single dating process. Remember I said there are 4 steps to the dating process. The first, you observe what's in the present. The second, you measure the rate at which change occurs. The third is you make assumptions. So the 3 assumptions, I've just given you some examples from the potato parable. Number 1, you're making an assumption about the constancy of the process rate. How constantly is the process occurring? Secondly, the degree to which the system has been isolated from the environment. You're making an assumption about that. You're making an assumption that the environment hasn't affected the system at all. And thirdly, you're making an assumption about the initial condition of the system. What did the system look like before it started changing? And all of those 3 things happen in the unobservable past, particularly when it comes to evolution. Millions and millions of years ago, and even if you're a new Earth or young Earth person, believe in the Earth being a young person, it still happened tens of thousands of years ago. So in order for you to come up with a correct answer, you have to make correct assumptions. And if you can't observe it, you can only assume. And so that's why they come up with data modelings. These are the assumptions that we're making, and we come up with a model based on our assumptions. So let me quickly give you an example based on the Niagara Falls. You know the Niagara Falls in America? So for those of you that don't, there's in the Great Lakes area, there is Lake Erie, which has a river that flows over the Niagara Escarpment into Lake Ontario. Okay, and so you can see the falls, there they stand. The falls can be measured currently. They're observably going backwards. They're retreating back into its gorge as the water flows over it and wears the rock away. So it's creating this gorge as it goes from Lake Ontario back towards Lake Erie as the gorge wears away with the water flowing over it. That can be measured to be happening at a rate of 4 or 5 feet a year. Okay. So there's a measured rate. Now, in the past, a guy called Charles Lyell, L-Y-E-L-L, in 1841, measured the rate of Niagara Falls' retreat, and he wanted to try and promote the notion of uniformity of geological processes, and it's largely been abandoned by scientists today as a notion, but that's what he was trying to promote. And he calculated based on the movement of that 3 or 4%, he calculated that Niagara was 35,000 years old, and therefore it predated creation, therefore creation is a load of bunkus, it's rubbish. But interestingly, he actually had to ignore the testimony of local residents that testified at the time that the falls were retreating at a rate much different from what they'd done in the past. In their observable lifetime, they were retreating at a different rate. So let's go back to some reality. If you assume that the falls started at Lake Ontario, where the existing cliff kind of basin thing is, where the gorge starts, then, and you assume uniformity of process, then, and I'll explain that in a minute, then the Niagara Falls are only about 9,000 years old. And even that's a bit spurious, because lots of things change the rate at which water flows. What happens if the rock strata is different? So harder rock wears out faster than softer rock. The same amount of water flow will wear sandstone away faster than granite away. Okay, so what happens if the water flow changed? In other words, the ice age happened, it melted, and you've now got massive runoffs of water. You've got more water flowing over the same rock, it'll wear it faster. So there's so many variables that are in that. So some scientists came along and they factored in all the rock strata and the types of rock, and factored in the ice age and the flow of water, the last ice age and the flow of water, and they came up with an age of the earth between 8,000 and 12,000 years old, which ties in actually quite well with the biblical narrative. A lot of people believe the earth's about 6,000 years old. We can talk about that afterwards if you're interested. Make a little note and ask me about it. That's a bit spurious. It's not actually accurate. It's probably closer to 8,000 to 12,000 years old. And as I said, if you're interested, we can talk about that afterwards. We'll cover that at some later point when we talk about a young Earth. It'll come up again. But if you're interested today, ask me afterwards and I'll cover it. So just there you can see the assumptions that are being made. If you assume that the gorge started way back there, then it changes. Maybe there was already a gorge, which is why the water's flowing off there. That changes the age. You're assuming the rock ages at the same rate. You're assuming the water flows at the same rate. You're assuming the amount of water hasn't changed. Amen? So lots of assumptions that all affect your aging process. Right, so I just wanted to give that as a bit of an introduction so we could understand the general concept of the aging process and the need for assumptions, because you're going to see these assumptions that occur in the two major dating methods. Let's talk about the dating methods. There are two primary dating methods that are used. One of those you may have heard, if you're a layperson, you may have heard of. The other one you probably haven't heard of unless you've read something specific about it. But those two dating methods are something called carbon-14 dating. You may have heard that. That's the one that most of us may have heard, comes up in movies and books and all the rest of it. And the other one is called radioisotope dating. Radioisotope is a less commonly known one, although within the scientific community it's very well known, but it's not sort of, doesn't come up in movies very often. I've never seen it mentioned in a movie. So I'm going to start with radioisotope dating, and then we'll do that one first, and then we'll do carbon-14 dating a little bit later on. I did say last week we were going to cover the Big Bang Theory this week, but just due to time, I'm going to put it into a session in 2 or 3 weeks' time. It fits logically there, and it gives us more time to do this. So let's talk about radioisotope dating. And this is where I need to get a little bit scientific, just so that we can understand what radioisotope dating is and how it works, so that we can point out where the assumptions are, okay? Right, so please forgive me if I'm mansplaining or science-splaining. I don't mean to be. I had to work my head around this at great length to try and understand what they're on about, and I still need to go look at notes to explain it. I can't explain it very well just off the cuff. Now, radioisotope dating. What is an isotope? Isotopes are variants of particular chemical elements. So if you remember from your science at school, you had the chemical, the chart of elements, the periodic table. So radioisotopes are just variants of those particular chemical elements. You don't need to know that. I'm just trying to give you some background. Now, there's some cautionary words that I need to deal with before I cover how this process actually works. First of all, when you look at these methods, radioisotope dating particularly, only rocks that have, the only rocks, radioisotope dating primarily dates things that were not organic, like rock. So it's not, they don't really use it to date trees that have petrified or fossils that have petrified. They use it to date the rocks around the fossil, okay? But it only works with rocks that were previously immensely hot and have now cooled, like magma, lava, that sort of rock. They don't work with deposit rocks, like sandstone, for example, because sandstone by nature is made up of millions of other pieces of rock. So sandstone, as other rocks break up and they form this tiny little bits of sand, and that all gets compacted into sandstone. So the radioisotope dating won't work there because it would have to work on the original rock that the sandstone came from. Does that make sense? So radioisotope dating only works on rocks that were liquid, molten, and have become solid, like magma from lava and those sorts of rock, okay? So something that was hot and is subsequently cooled. People believe that the reason it works is because that heating to cool resets the radioisotope clock. So it starts running from zero again, or at that point. So it's the only place it really works. So sedimentary rocks such as limestone, sandstone, shale cannot be dated. Right, so the first radioisotope dating technique, which was well studied and well researched and has formed the basis for all others, is based on the fact that there's a radioisotope called uranium-238. It's a form of uranium, and it's a very unstable radioactive element. And it decays spontaneously, so it naturally decays. And it naturally, as it decays, it becomes something different. It becomes lead-206. So this particular uranium-238, as it decays, it naturally turns into lead-206. It becomes something different, okay? So all radioisotope dating is based on elements that go from one isotope to a different isotope as it decays. As it rots or changes or ages, it rots the wrong word. As it ages, it transforms into a different element. Does that make sense? Okay. And there's a variety they use, but the original one, and it's the one that set all the science in place, was this uranium to lead. So let me cover the process basically quickly for you. Each time an atom changes into another atom, so uranium to lead, it gives off a certain amount of energy. And that the level of that energy can be measured. So a specific decay period can be recognized. As that energy is given off, they can recognize decay happened because energy was given off, yeah? So uranium, in the process we're talking about, is called the parent, and lead is called the child. So in radioisotope dating, there's always a parent and a child. In this instance, it's uranium and lead. And so as it processes through what's called the daughter, not the child, as it goes through this change from uranium to lead, it happens at a particular rate, a fixed rate. And the rate at which that changes is observable and measurable. So this particular uranium to lead has been measured for decades. It's very precisely measured and very accurately measured. Now, another term you may have heard, it's called the half-life of uranium. So the half-life of uranium, or in any product, is the time in which it takes half of the original mass to become the other mass, half of the parent to become the daughter. So if you have 1 kilogram of uranium, how long does it take 1 kilogram of uranium to spontaneously, naturally deteriorate and become 1 kilogram of, and become half a kilogram of lead. So you've got half a kilo of uranium and half a kilo of lead. That's called the half-life, okay? How long does it take this to go from being full uranium to half lead, half uranium? So if you can measure in rock, if you can see that there's uranium and lead in the rock, then you can see this process has taken place in one way, form, or another. Now, you need to bear in mind that the measurement of a half-life is not a measurement of time, but it's a measurement of the rate of decay. But that's by the by for us. So simply stated, when a scientist wants to age-date a rock, they must first measure the present state of that rock. This means measuring the amount of each of the effective isotopes in the rock. How much uranium's in the rock, how much lead is in the rock. And that's the measurement of the present state. They know from scientific observation the rate at which that changes. So the second step has been done. Yeah. And they then have to answer some questions or make some assumptions about how long the process has been in operation so that they can observe, they can make some conclusions as to how old the rock is. Right. We've looked at those assumptions. So let me apply those assumptions. And there's 4 assumptions they make about with radioisotope dating that are important for us to get our head around. The first assumption requires an assumption on the constant rate of decay. Okay, is it scientifically reasonable to assume that the decay rate hasn't changed over billions of years when we've only been measuring it for a few decades? Is that scientific? Can we assume that it's always been the same rate of decay? Now, the decay rate hasn't changed at all in the time we've been observing it. So scientists have performed all sorts of experiments on it to try and encourage the rate to change. They're using changing conditions that might occur in nature, and it's been observed to change in very, very, very small fractional amounts when impacted by outside things. So really, it's not such an issue. The half-life, by the way, of uranium to lead is 4.51 billion years old, which is why that is the current preferred age of the universe. Because if you believe in radioisotope dating and you swallow the assumptions, then and you can see that there's uranium and lead in a rock, then it must be at least 4.51 billion years old, because that's the rate. If you take the existing rate it ages or decays and you work it backwards, that's how old it has to be. Now, we would have to grant that, with some reservations, but you'd have to grant that the probability that the rate of decay has remained the same is probably accurate. So in this instance, the first assumption they're making about the rate of decay is probably accurate. It probably hasn't changed. We've not been able to cause it to change in any way, form, or fashion, but there is some reservations because it's not been observable in the past. We don't know what happened in the past. In our environment, our world, we can't cause it to change. So let's give them the fact that the rate of decay hasn't changed. The second assumption regards the degree to which the system has been isolated from the environment. So, is it scientifically reasonable to assume that neither the parent nor the daughter concentrations, nor any of the intermediate products, some of which are highly mobile gases, have been altered throughout the entire history of the rock, except by radioactive decay, or that the amount of loss or gain can be known? Can they make the assumption? Because listen, it doesn't go straight from uranium to lead. It goes through a whole bunch of other stuff in the way there. It winds up as lead. And some of that processes are highly unstable gases. And is it safe to assume, is it scientific to assume that none of those processes react negatively when influenced by its environment? So the second assumption is a little less reasonable than the first. It has some serious problems. It is true that when scientists gather, and bear with me here, I'll try and explain this to you. When scientists gather core samples, so they drill cores out of rock, that they try and exclude any samples that show obvious contamination, because otherwise it skews their data, because obviously it's contaminated. So they then wind up with a whole bunch of test subjects that show no form of obvious contamination. They then test them. Any core that they're testing that comes up with spurious results, they now assume that it's contaminated by something they can't observe, and they exclude it. So their results are based only on the data that gives them the results they want. Anything that doesn't give them the results they want, they assume as being contaminated. But it does beg the question, how do you know that the results, the core data that you're looking at, hasn't been itself contaminated? In other words, that the whole process has not been affected by something outside the environment. You're assuming if you start off with 20 cores and you exclude 3 of them because they've got some form of observable contamination on them, and so you test 17, and of the 17, 5 come back with weird data, so you exclude those 5, and you're now only left with 12. How do you know that those 12 aren't contaminated in a way as well that's giving you false data? They're just all giving you the same false data. You don't know that. By agreeing that outside environment will contaminate your core samples and you can therefore exclude them, you're kind of opening the door to say you believe that the environment can have contaminated your system. You just can't prove that the ones you're using were contaminated in any way, form, or fashion. Okay, so that's the problem we have with the second assumption. The third assumption regards the initial condition of the system. Is it scientifically reasonable to assume that the original quantities of the various isotopes, uranium and lead, particularly the amount of lead, the daughter, was a null value? Is it scientific to assume that when this rock formed, there was no lead in it? Therefore, you can now assume that all the lead that's there has happened because of the decay of uranium, therefore it's at least 4.5 billion years old. And this is the real Achilles heel of the radioisotope dating method. It is massively spurious as a scientific exercise to assume that there was none of the daughter element in it. Some of the daughter element present in the start of the rock would already appear to be old when in fact the rock was just formed. If you picked up a rock and you found some lead in it and your assumption was there was never any lead in it to begin with, you're assuming this rock is billions of years old when it might actually be a week old. Okay? Now, let me give you some examples. You can gather some. Remember I said radioisotope dating works on magma type rock that was hot. So we have lots of volcanoes, and you can go to those volcanoes and you can pick up the rock that has just been formed, brand new rock, and you can test it. And if their assumption is correct, there should be no daughter elements in that rock because it's just been formed. It's days old or weeks old, yeah? So there should be no lead in it, no daughter element, and no lead in particular in this instance, because lead takes 4.51 billion years to decay from uranium. So you should have lots of uranium and no lead. Okay, let's look at some examples. The Sunset Crater in northern Arizona is a recent volcano. Okay, Indian artifacts and remains are found within the rocks formed by the volcanic eruptions, first in the form of lava flows and then in the form of cinder showers. Few of the inhabitants seem to have been killed by the eruption, but their villages and agricultural sites were buried. The Indians hastily moved to a safer location, but took with them the tale of the mountains activity. So within the American Indian culture and law, there is this notion of this volcano that exploded, Sunset Crater, and in their law, in their history, it happened 900 years ago. So we know from observable history that 900 odd years ago, this volcano exploded. Yeah? Tree ring dating. So when you look at the rings of a tree, that's a very accurate form of dating something. So tree ring dating, found within the rock forms, the lava, accurately dates the eruption to have happened in 1065 AD. So we know from tree ring dating that in 1065 AD, this thing exploded, this volcano. The Indians believe that it was about 900 years ago, so the two coincide really well. Much to everyone's surprise, when the magma, the rock, was dated with radioisotope dating, it was found to give an age of 210 to 230,000 years.
Oh.
Which means there was some daughter in the rock originally. It gets more interesting. A similar error would be could be cited if you look at the eruption of Mount Rangitoto in New Zealand. I think I pronounced that right. It was dated by radiocarbon studies of destroyed trees to be less than 300 years in age. Potassium argon, which is another form of radioisotope dating, like lead, uranium lead, potassium to argon is another form of radioisotope dating, dates it at 485,000 years. Clearly, we have a problem with the assumptions. And then this is the kicker for me. In Hawaii, there's and I can never pronounce Hawaiian names, it's the Hualaiai volcano on the Kaopelelehu flow. Forgive me. They were known to have erupted in 1800, 1801, okay? But were dated with a variety of methods, looking at various isotopes and coming up with various conclusions. Now, it's too young to have produced much radiogenic argon or helium, which is another types of isotope dating. The rocks contain large amounts of those data within them, although they're too young to have produced them, those daughter elements. The article reports, in the dating article, 12 dates that they've come up with, okay? This thing exploded in 1800, 1801. And the dates range from 140 million years ago to 2.96 billion years ago. So clearly, the radioisotope dating doesn't work well.
Yeah.
Because the assumptions that are being made are wrong. Okay, and it's these assumptions when scientists stand up and say, this tree is 3.5 billion years old. Rubbish. You're making assumptions. And those assumptions have proven observably to not be accurate. Okay. And now, I know we had 3 assumptions in the original dating process. I want to just kick a 4th one in at this point. It's an additional assumption, which is in actual fact an overarching backdrop for the whole method. And that is the assumption the Earth is at least as old enough to produce the present amount of radiogenic lead in a specimen to have produced the present rates of uranium decay. That's why they believe that the Earth is at least 4.5 billion years old. The Earth has to be that old because otherwise it couldn't have happened. The assumptions don't work. But maybe God created rocks with parent-daughter mixes of things in it. Excuse me. So to sum that radioisotope dating up, it assumes that radioactive dating assumes uniformity. It assumes that there's never been a world restructuring catastrophe, like perhaps the flood. And that it also assumed that there was no supernatural creation, which assumes the Earth to be very old. So they're making a whole bunch of assumptions that aren't observable. And remember what I said in the beginning, we can't prove the Earth is young. We take it by faith. But the scientific evidence, when correctly weighed, seems to indicate a young Earth as opposed to an old Earth. And there's an enormous amount of scientists out there that are not Christians that are young Earth scientists. They believe the Earth is young because they've looked at the data in a correct manner. Okay, so let's talk about carbon-14 dating. So that's radioisotope dating. Carbon-14 dating will take me a lot less time to cover. Many people have an incorrect notion that carbon-14 dating places the age of the Earth at billions of years old. That's incorrect. It's radioisotope dating that places the age of the Earth really old. Carbon-14 dating is really just a form of dating that works very well for relatively recent times. Even the most devoted advocate of carbon-14 dating would not claim that it has anything to say about the age of something beyond about 60,000 years. Beyond 60,000 years, even the most devoted advocate will say, you can't use carbon-14 dating to date something that conceivably that old. But if you're going to use carbon-14, on the other hand, carbon-14 dating to date something that is a few thousand years old, it can be very, very accurate. Okay, so it can work really well if you date a Viking's slipper from 3,000 years ago. That'll work. If you date an Egyptian pharaoh's bones from 6,000 years ago, that would work. Then it becomes much more accurate in its approach. Okay, so the standard assumptions are valid. They assume that the rate of carbon-14 decay is constant. They assume that there has been no additions or deletions of the daughter parent materials. And they assume that the amount of daughter materials present in the product at the beginning was 0. Okay, so they make those same assumptions, and therefore they're just as flawed as the first method we dealt with, radioisotope dating. However, if you assume those and work around those, it can tell us something about sort of specific dates of historical artifacts that can be quite helpful. So what's important for you to recognize is that carbon-14 dating only works on things that have carbon in them. In other words, something that had matter, the organic world. The inorganic world is dated, in other words, rock is dated, and only melted rock, not sedimentary rock, is dated by radioisotope dating. The organic world is dated by carbon-14 daters. All organic life, plants, humans, animals, have carbon in us. Carbon is part of our makeup. And so rocks don't have carbon in them. So carbon-14 dating only dates things that at one point were alive. Trees, materials, fibers, plants, humans, animals, those sorts of things, yeah? So a tree that was buried in lava, the tree can be dated by carbon-14 dating, and also by tree ring chronology, it can be dated that way. But the rock can only be dated by radioisotope dating. So the rock will tell us it's yay many years old, the tree will tell us it's a different age. So just bear that in mind when you think about carbon-14 dating. So let me explain carbon-14 dating to you really quickly. Carbon-14 is formed when nitrogen-14 is altered in the atmosphere that we live in. So when we eat something, or we breathe something in, or drink something, an animal or a plant or human, when they interact with nitrogen-14, which is found in the atmosphere, carbon-14 results. And it's a radioisotope, radioactive isotope, and it's a tiny, tiny percentage of all the carbon that exists within us. So it's a small little percent, so it's nothing you need to worry about. The ratio of radioactive carbon-14 to stable carbon, which is carbon-12. So we're all made up of, majority of us is stable carbon, carbon-12. Carbon-14 is a tiny little amount, it's radioactive. The ratio can be very accurately measured. So they can observe in the present, they can say a human being has this much ratio, an animal has this much ratio, this is the ratio in a vegetable, yeah? Any life form, they can, in the present, they can observe the ratio between it very accurately. And both forms of carbon are distributed throughout the atmosphere, the oceans, the earth, they're all over the place. So once a plant or an animal dies, it ceases to interact with the atmosphere, stops breathing, stops consuming, okay? Therefore, it stops taking nitrogen-14 in to convert it to carbon-14. So you've got no carbon-14 being created. So the ratio begins to change. The stable carbon, carbon-12, and in a living organism of the same type, you can measure the ratio between carbon-12 and carbon-14. Carbon-14 is created when you interact with nitrogen-12, yeah? But when you stop breathing or drinking water or eating food, you're no longer interacting, so carbon-14 no longer is formed. Therefore, the ratio diminishes. You have less carbon-14 in you and more carbon-12 in you. Does that make sense? Yeah? No? Vicky's not shaking her head, she's just sitting there. So let me try and explain it again. Carbon-14 occurs when you breathe air, eat food. It comes from nitrogen-14, which is in the atmosphere around us. So as we react with nitrogen-14 in the form of consuming it or drinking it, it becomes carbon-14 in our bodies. And when you're alive, that ratio remains the same. Carbon-12 is what we're made of, and it's stable carbon, and carbon-14 is something we put into us with our environment. So if we're living and breathing, and it doesn't change if you eat more than the next person. It's, if you're alive, you have a certain amount of carbon-14, which is created because you're alive, because you're breathing and eating, and carbon-12, which is stable within your body. When you die, you stop breathing and eating. So the amount of carbon-14 diminishes in the sense that it's no longer growing, it's no longer being resupplied. So as that body is now dead for 1,000 years, the carbon-12 stays the same, but the carbon-14 is less than it should be for someone that's 1,000 years old. So that's how they measure the difference in the ratio. They can measure how old something is. Okay, that's basically how it works. Now, many processes can occur, such as groundwater leaching, bacterial action, which can alter the concentration of the parent or daughter material, carbon-12, carbon-14. Much can occur. And so care has to be taken, and usually is taken by scientists. To date, only those specimens which give no appearance have been contaminated or leached. Carbon-14 decays at a rather stable rate and has been shown by precise measurements, but the assumption of the original concentration of the parent and the daughter is once again its Achilles heel. My potato parable. You don't know how many potatoes were in the basket, peeled potatoes, to begin with. The same problem with radioisotope dating exists within carbon-14 dating. So to sum carbon-14 dating up, generally speaking, it can be quite accurate, but we don't know how much carbon-14 was originally in the body to begin with. We have no idea. So it's problematic. And that's why it'll go out to maybe 60,000 years old. I believe the Earth is 10 to 12,000 years old, but because of those erroneous assumptions. So, conclusion, dating methods have some scientific value, but their results are often massively misleading due to preconceptions by the scientist. The scientist makes some assumptions about things that he doesn't want to consider realistically. And that's why you have a lot of young Earth scientists now that believe in the Earth as being 10 to 12, 25,000 years old. Okay, I'm going to stop there and open the floor for any questions. If anyone wants to ask anything, if you could just switch your microphone on and ask, that'll be great. Everyone clear as mud. Sorry, that's as scientific as I'm going to let it get. But and as you can see, unless you explain how the process works, you can't understand what's wrong, because you need to understand what the assumptions are. And I really found that potato example massively helpful. Yes.
Yeah. When you were explaining the carbon-14 dating.
Yeah.
I would, if as soon as people start talking about chemicals and things, my mind just blanks out. So how I think of it is, let's say you've got colors in your body,
yeah,
and the blue is constant, and when you die, it'll still be that blue in a million years' time. But the pink in your body, the red will gradually seep out and seep out and seep out, so that pink will get lighter and lighter and lighter. Yeah. But you don't know how pink it was to start with.
And that's pretty accurate. Perhaps the better way of explaining it is the blue will remain static, but the pink is maintained, the level of pink. So if you have 1 liter of red, 1 liter of blue and 1 cup of pink, the cup of pink is maintained at a cup. by the fact that you're interacting with your world. You're breathing and eating. So the minute you stop breathing and eating, that pink cup doesn't stay topped up. And so it diminishes in the sense as the organism, the carbon continues to exist. You're not aging anymore, but the carbon is still there. And so the ratios between how much was there, it differs. But as you said, we don't know how much was there to begin with. So
that's really interesting. Yeah, thank you.
I think the important thing to take away tonight is, as I said, there's some scientific value in the dating processes, but please don't take it to the bank. And there's much to this. I mean, you know, Einstein believed that the world was 10 billion years old. Other people today believe that it's, you know, 4.5 billion. Others believe that it's 20, 30 billion. So there's really no basis on which they're making that assumption. The only people that make any sense to me are the people that are saying, I'm doing it based on radioisotope dating. I disagree with you doing it that way, but at least you're making an intelligent assumption on its age as opposed to thumb sucking. But as I said, there's massive assumptions that you're making in that whole process.
I've got a question.
Yeah, go ahead.
So if we're saying there's like inconsistencies with the radioactive, the isotopes dating, what about the isotopes that have shorter half-lives that we can actually study, like for instance, like 5 days or 2 days?
It's a really good question.
If these are accurate, it kind of...
It's a really good question. The problem with something that has a shorter half-life is it doesn't support the notion that the Earth is billions of years old. Because then the Earth would only be 5 years old. Do you understand? They need something that has a massive half-life because that plays into their thinking of the evolutionary model. They need to be able to say this happened over billions and billions of years. Otherwise, evolution can't have happened because the concept of evolution is that it happens in the species over massive amounts of time. So they need to be able to take something that ages really, really slowly. I also think, and again, I'm not a scientist here, so I may be talking completely erroneously, but I think things with shorter half-lives don't really help you because they will, if you have a cup of red and it becomes half a cup of pink and half a cup of red in 5 days, in 10 days there's no red left and you have a cup of pink. And now you don't know how long that has been pink. So you need to be able to measure something that's old enough that you still have some of the parent there as well as some of the daughter. So you need things with a long half-lives. That's how I understand it, but I stand over to be corrected on that, Merville. You need to remember that scientists are not trying to prove whether or not evolution happened, in the sense that this is a theory, let's see if it's true. They're assuming that it happened and trying to prove it on that basis. They're not approaching it and saying, let's look at the facts and see whether young Earth, old Earth, intelligent design or pure chance. They're not doing that. They're working from the basis, I don't believe in God, that's fantasy, therefore there is no creation, and the only alternative is evolution, so that becomes my starting premise. Therefore, I must find a solution that fits the model that I adhere to. Which is why I said Dr. David Block last week, when you look at him, he said there's more evidence for creation than evolution, more scientific evidence. Not that creation is a science, but the reality is the world around us points at the fact that there is a creation. And if scientists are just going to be a little bit scientific, they're going to have to acknowledge that all these assumptions are erroneous because, as I said, you can look at volcanoes that we know are 100 years old or 200 years old or 900 years old, and they're dating them as billions of years old. So clearly the assumptions are wrong. But they're not willing to do that. And those that have come to the conclusion that the Earth is young. It's not old. It's a young Earth, based on all the other, which is one of the outside factors, which is why I was talking about Niagara Falls. You know, if you look at it in a linear fashion, then it's 35,000 years old. But when you factor in all the conceivable differences and outside influences, you know, then it's 8 to 12,000 years old.
So, Pastor Sean, how do they allow all these things in the textbooks if there are so many assumptions, so many ways to prove that, you know, that like all the calculations are not right? How is it allowed in educational books?
Because you aren't allowed to question it, Kenny. It's the same way as if I stand up today and start questioning the fact that you can choose your gender, then I'm censored. It's hate speech. Do you understand? So we censor those voices. And let me say this, lots and lots and lots of scientists don't believe in evolution. But there's an agenda here that is satanically driven. And I'm not the sort of person who looks for demon behind every bush, but the devil wants to confuse the issue. So using the liberal press and the liberal side of things, they don't want people to acknowledge that there's an issue. So you have a look. If you have a look at some of the archaeological discoveries that occurred in the Fertile Crescent, Abraham's time, okay? There's massive amounts of massively influential archaeological discoveries where they found libraries full of tablets with records on them, but no one's allowed to access them. Why? Because they're in the Arab world. So the devil doesn't want Jesus to be proven to be true. He doesn't want any scripture to be evidenced. And it's an interesting, I read one scientist once say that the Bible is not a book of science, but every place that science, how did he put it? Science has never proven the Bible wrong. You can't prove that creation didn't happen. You can just come up with an alternative theory. So science supports the Bible where science works, but science isn't complete and comprehensive yet. So yeah, I don't know why. It's as I said, it's the same reason perhaps why we can't speak out against homosexuality or speak out against gender dysphoria. We can't speak out against anything that the liberal side of our society is shouting about. And it's terrifying because liberals have become the most bigoted people on the planet. As long as you agree with them, you can have any opinion you want. But if you disagree with them at all, they riot, they throw petrol bombs at you. You know, it's Nazi Germany, 1936.
Sean, on that topic, did you see the news article in the Times in Scotland that they want to, some newspapers and books and the Bible, they've starting a new bill that they want to ban it completely? No, because they say it's under the hate speech criminal law.
They haven't. I haven't seen that. But there's an agenda. There's a worldwide agenda. The devil is working through those people that he has influence for. And to me, that it's the most. I've lived through wars. I've lived through terrorism. It's the most scary thing is that I'm not allowed to have an opinion anymore if it differs from yours. Unless I agree with you and you, the liberal, you aren't allowed to have an opinion. You aren't even allowed to question it. You aren't allowed to question anything that happens. If it goes against the flow of what the popular press is saying, then you aren't allowed to have an opinion. You aren't allowed to question it. You can't ask a question about anything. Then you're a bigot and a homophobe and a misogynist and a racist and all sorts of stuff, just because you ask questions.
It's funny how they can always question though.
Yeah, but you see, this is the thing about the liberal side of things. I listened to a really interesting documentary a couple of weeks ago. It wasn't a documentary, it was a video of a person, a lesbian woman, being lesbian. She considers herself what's called a gold star lesbian. In other words, she's never had any involvement with men whatsoever. And she said something really interesting. I listened to it because of what she said. She said she 20 years ago, the only place the lesbian or gay community could find a home was amongst the liberals, because the conservatives were saying, no, you're wrong. And the liberals are saying, no, come and be anything you want. We're not going to judge you. She said now she finds it the opposite way around. She says that she now finds the conservatives are saying things like, you know what, we disagree with you, but as long as you leave us alone to live our lives, as long as I can have my opinion, you can have your opinion, that's fine. That seems to be the general consensus in the States amongst the conservatives. Whereas the liberals are saying, no, You do it my way, or there is no other way. So, for example, she's a YouTube influencer, and she asked the question. She showed a picture of a man with a fully bearded face who was claiming to be a woman, and she said, "This is not a woman." And the transgender community came down on her like a ton of bricks. And then the rest of the LGBT community came down on her as a ton of bricks. And she was like, no, you can't say someone that looks like a man, walks like a man, talks like a man is not a man. It's a man. You know, the DNA is there, the genetics are there. But because she had a differing view, absolutely, her channel was demonetized. She was pilloried from, and she now considers herself to be a conservative lesbian American. It's the times we live in. The most intolerant people today are liberals. Anyway, this is an entirely different matter. And I'm going to edit this off the back of the tape before I put it on the internet. Otherwise I'll get into trouble. I'll have a bunch of raving loony liberals outside my house here. Does anyone have any questions? Anything else about the lesson today? No? We all happy? Great. Next week, we're going to do the marriage between evolution and creation. In other words, what have Christians tried to do to make the apparent scientific evidence of evolution fit into creation? And so there's two main theories. It's called the gap theory or the long day theory, and we're going to look at those and see what's right and wrong with them and how they tie in with scriptures. So that'll be next week.
Excellent, thank you.
It's scientific. Guys, if you need to chat about it, if you're confused about anything or you want to ask, please just give me a bell. We can have a chat, have a Zoom meeting. No problem. I'm happy to do that. Amen.
Thank you.
God bless you all. Stay safe, stay well. Enjoy the rest of the week. See you at church on Sunday.
Bye. Bye. Bye.